Hello and welcome back to the Free Science Channel Artificial Intelligence Lecture Series. In this video, I'm going to teach Recurrent Neural Network Architecture, which is the advanced section in Artificial Intelligence Lecture Series. This video covers Part 1, which is an introduction to Recurrent Neural Network Architecture, and solid understanding of deep learning is a prerequisite of this course. I'm going to turn off the camera and start teaching. The learning outcomes of this video are listed here. In this video, we'll learn the concept of sequential data. What is a sequential data and how this type of data, the sequential data, can make a challenge for fully connected neural networks. And after discussing these challenges that fully connected neural network have with sequential data, sequential type data, the configuration of the recurrent neural network will be introduced, and it will discuss how recurrent neural network deal with these challenges. And the vanilla recurrent neural network will be introduced, which is the simplest configuration of the recurrent neural network. And finally, some applications of recurrent neural network will be discussed as an example at the end of the video. What is a sequential data? If we get a data and we see the dependency between the data points, between point 1, point 2, until point M, if there is a dependency between these points, then this type of data is sequential data. As an example, we remember from the physics that according to the Newton's law, we can write v velocity at time step 1 equals to velocity at time step 0 plus delta x time t1. This equation shows that the value of velocity at time step 1 depends on the value of the velocity at time step 0. Following the same equation, we can write for data point 2, velocity at time step 2 equals to velocity at time step 1 plus delta x2 t2. Again, the same concept. The value of the velocity at time step 2 depends on the previous value of velocity at time step 1. And for all of the time steps, generally we can write velocity at time step n equals to velocity as previous time step plus delta x n time t n. Here 3 is wrong, it should be delta x n. You see the dependency between the data points. If we are given a velocity data points, we see the dependency between the data points, and we can say that this type of data is sequential data. Let's review some more examples about the sequential data. If you work on a text analysis projects, you would see this issue a lot. For analysis of the text, for example, if you work on the auto-completed text editor softwares or translator platforms, you will see that. You must have worked with auto-completed text editors in your mobile phones. Today is available in all of the phones. In the text editors, auto-completed text editors, if you write, for example, there are examples. If you write, I had not been there yesterday, this adverb will be offered by the text editor or the completed text editor. And if you write, I will arrive there tomorrow, this adverb will be offered by the completed text editor. You see how the adverb here, yesterday, depends on the verb which is used here. And also dependency of tomorrow, how it is connected, how it depends on will arrive. You see that how different words in one sentence are depend on each other. This also is could be seen as a sequential data. These kind of texts could be seen as a sequential data, and you clearly see the dependency between different part of the sentences. For text translators, one example of the text translation. If you write what time is it in Google Translator, the meaning that you get from Google Translator is very different by this part. It is what time. And you see that by changing the order of the words, we have 1, 2, 3, 4 words here. If you change the order of these words, you will get different meanings out of the sentence. Again, this is another type of the sequential data, and as I discussed it before, different part of the data, different part of the sentence depends on each other. So working with sequential data, processing the sequential data with fully connected neural networks, it is challenging. And here I want to discuss these challenges that fully connected neural network have in processing the sequential data. The first challenge is fully connected neural network needs fixed length of the input. Imagine you remember this velocity, that velocity equation that we had. N at time step n equals to velocity at time step n minus 1 plus delta x n multiplied by time. If we plot two data points, the velocity profiles, one with 20 data points, the blue curve with 20 data points. If you count the dots, the blue dots, you see that there are 20 data points showing the velocity profile on blue curve. And here we have 7 data points. And we want to introduce these two data to the neural network and get prediction. Then we expect the model predict the velocity, for example, at the next time step was. If we do so, it means that we need a neural network that can make a prediction using 20 values we have for the blue curve and make a prediction using 7 values we have for the orange curve. I assume that we have a neural network here, the fixed architecture of the neural network, and here we have inputs. 7 inputs are introduced to the fixed architecture of neural network, and we will get output of it. By the fixed architecture, we cannot introduce 20 data points and get prediction out of it. We should make changes in the architecture of the neural network because we just can have 7 inputs to the neural network, and this should be adapted to the 20 data points. The same issue we have for convolutional neural networks. Convolutional neural networks also need a fixed length of the input. You see, by the fixed architecture of the neural network, we cannot receive data points with different lengths. It is the first challenge that fully connected neural networks have in processing sequential data. For the same challenge, let's review one example by text analysis, about the text analysis. Suppose that we have what time is it, and we want to introduce it to our fixed architecture of the neural network and get output of it. What time is it includes 4 words. What time is 4 words? And we need 4 nodes in the input, and we introduce it to the neural network and get output of it. What if at the next step we introduce how much does it cost, and we want to ask our neural network to predict the meanings of these sentences. If we introduce how much does it cost, include 1, 2, 3, 4, 5 words, and we need input with length of 5. So it is challenging. We cannot do it unless we change the architecture of the neural network. Maybe you answer me, you will make an input with 1,000 nodes and input. And for first example, what time is it? For the first example, you will use 4 of these nodes, 1, 2, 3, 4, for example, and keep the rest 0. And so introduce what time is it to your translator and get output. And for the second example, you will use 5 nodes out of 1,000 and keep 995 0 and introduce your input the node. By this approach, if you make an input with 1,000 nodes, this approach may work, but it's not efficient approach. I usually do not do so. I think then the next limitation of the neural networks is computation costs. As you know, neural networks do not work with the strings and text, and we should convert our text to the vectors. There is a method called one-hot encoding, and the idea in one-hot encoding is, for example, it is, we say, for example, we have 10,000 English vocabulary totally. I'm not sure how many vocabularies in English we have, but it's just an example, maybe 30,000, maybe 50,000 vocabularies. And we make a vector with a length of 50,000, for example, or 10,000. Here I use 10,000, the length of the 10,000. And for what, we add 1 to the second entity of the vector and keep the rest as 0. And for time, for example, we add 1 to the middle of the vector. For example, it is 5,000 entity of the vector and keep the rest 0. And for ease, the first entity, we add 1 and keep the rest 0. And for it, for example, we add 1 at the last entity and keep the rest 0. By this method, we can convert our words, our sentence, to the vectors. And now these vectors will be introduced to the neural network. This method computationally is expensive. Remember, each word that you introduce your network has 1,000 entity. Each vector has 1,000 members, 1,000 items in it. is has 10,000, is has 10,000, it has 10,000, time has 10,000. One of them is 1 and the rest are 0. And after introducing this input to the neural network, this input should be transferred to the next hidden layer and to the next hidden layer just in forward propagation, in back propagation. And it includes lots of parameters and lots of calculations, and computationally is very expensive. Therefore, using analysis and processing of the sequential data with neural networks is challenging, not only because of the fixed length of the input, but also because of the computational cost. There is another reason that we do not select the fully connected neural networks as a suitable candidate to process the sequential data. This reason is in a fully connected neural network, parameters are not transferable. Fully connected neural networks do not share the parameters, and parameters are not transferable. An example, I have an example here. If you ask your neural network to translate Sarah saw you today, you input it to your neural network and get output of it. And so in whatever language you want to output it, for example, let's say you translate English to I don't know, Indian language, and get output of it. If you change the order of the sentence, it is the first input that you introduce your system. If you change the order and introduce today's Sarah saw you, you should get the same translation out of it. The context will not be, both of sentences, one and second, have the same meaning, but there is just the difference is here. There's an emphasis that Sarah saw you today, but the second sentence, today, the emphasis is on the time. Today, Sarah saw you. If you use neural networks, for the first sentence, we need to run our neural network and get output out of it. And for the second sentence, again, we need to rerun our neural network. It means that, for example, at the first example, when we introduce Sarah saw you today, Sarah will be processed by the first node, for example, and today will be processed by the last node. And if you change the order of the sentence and introduce today Sarah saw you, today will be processed by this node, and Sarah will be processed by this node. Because the parameters are not transferable, are not shared in fully connected neural networks, the parameter from this node will not transfer to the first node for today. And we need to rerun the neural network again. And this is another challenge that we have in working with sequential data when we have fully connected neural network. Maybe you say for convolutional neural networks, the convolutional neural networks have the ability to share the parameters. Okay, it is true that convolutional neural networks can share the parameters. Maybe we do not need, if you change the order of the sentence, we do not need to rerun the model again, but convolutional neural networks need fixed length of the input. The first challenge that fully connected and convolutional neural networks both have this challenge in working with sequential data. How to cope these challenges? How to deal with these challenges? The solution is using recurrent neural networks. In recurrent neural networks, we have an input like xt. xt could include different features, for example, x1 to x2, 3 to xn. And output is yt, and yt also could be y1, y2, and to yn. The important part of the recurrent neural networks is feedback loop, this part that add the flexibility to the network, that network can work with different lengths of the input. In recurrent neural networks, each features of the input, for example, here x1, x2, x3, and xn, are introduced to the network over and over. That's why it is called recurrent neural network. And as you see, each feature can have one output, like y1, y2, and each output has its own loss. And for total loss, we need to sum all of the losses. If we show each item of loss by Li, I1 to n, we will get total loss, as it is shown here. How mathematically recurrent neural networks are shown? The parameters mathematically, if we assume that we have WIH for the input and WYH for the output and WHH for the internal for the hidden layers, we can mathematically show recurrent neural networks like this. If we say we have a box like this and we have a xt, this xt has a parameter called IH, and we have a hidden layer. This cross shows the multiplication. The hidden layer from time step ht minus 1 times by WHH, and the result of these two will be summed with the bias, and the result of this sum will be introduced to a tangent hyperbolic as a activation function. And here we have two outputs. One output goes to the next hidden layer that we can show it by HT, and the other output goes to the Y, is shown with Y. We can show it by YT, and here we should have another activation function. Like softmax, for example. This activation function here is shown with alpha. Here, this alpha, for example, could be softmax. As you see, the output of each hidden layer transfers to the next hidden layer, the next hidden layer, and each hidden layer can have one output of y1, y2, y3 up to yn. Mathematically, the hidden layers are shown with this equation, and the output of the hidden layers also, the y's, I mean, are shown with this equation. Let's give you some examples of the recurrent neural networks. I mean, where we usually use neural networks. Neural networks can be used in different situations, and they can have different configurations. One configuration, the first configuration that here I want to discuss is we can have one input to the to our RNN and have a sequential output. The example of this configuration is image captioning. Here we introduce one image to our RNN and we get a description out of the model. The model adds a caption to the picture, describes, interpret the picture, the image for us. As you see, here we introduce one single image and we get a sequential data, some text about the image. The other example could be reverse. It could be completely different by the first example. We can have a sequential data as an input, a vector introduced to the will be introduced to the RNN, and we get one single output of it. The example of using this configuration is sentiment analysis. As you see, we have some sequential words, a text, a word will be introduced to the RNN, and in the output, we have category of sentiment. For example, is happy, is not happy, or some other options. The next example that I want to discuss here is we can have sequential data input to the recurrent neural network and sequential output, vector in, vector out. We can introduce a vector to the recurrent neural network and get a vector out of it. The example of this configuration is grammatical tagging, that some sequential words are introduced to the recurrent neural network, and as an output, we get category of each part of the sentence that we have. The other example is encoder-decoder, that is very popular method in language translation. Here we can have some words, a vector introduced to the recurrent neural network, and some words out here. Yeah, it's a special part of vector in, vector out, and then this part will be encoder, and this part will be decoder. Here is the end of the first part of recurrent neural network, and if you want to know more details about the recurrent neural network, you can follow this part 2 of the recurrent neural networks in this channel.